Dear students, in this class we will just see how a tension test is conducted on a mild steel specimen or any specimen of material. Here, this is the specimen under consideration. Initial length I have taken L1 and it is subjected to pull force, that is tension force P in the machine. That machine, whatever we are going to conduct tension test, it is called as universal testing machine. So you can conduct tension test, compression test, shear test, bending test, all those things in that machine. That is why it is called as universal testing machine. So specimen is kept in that and load is applied like this. Slowly, gradually load is applied. So when it is subjected to tension load, so elongation takes place. The length of the specimen increases. So I have taken the final length till the failure. So this is the failure of the specimen. So till the failure occurs, we are slowly increasing the load acting on the specimen, and at certain point of time, failure takes place like this. So you have to note down the length of that specimen at the time of failure, after failure. So here, these 2 points, A and B, they are called as gauge points, and this length is called as gauge length. So L1 is called as the initial gauge length, L2 is the final length of the specimen. So as you observe here, in this case, in the tension tester, length increases but diameter reduces. Diameter reduces means here L2 is greater than L1 but D2 is less than D1. Diameter reduces, shear force is D2 is less than D1, area will be area reduces, that means A2 will be less than A1. Now we are in this type of problem, they will ask certain things, that is what is the percentage increase in the length or elongation, percentage elongation, what is the percentage reduction in the area. So percentage increase in length we can calculate using this formula, final length minus initial length divided by initial length into 100. Percentage reduction area is given by A1, that is initial area minus final, because area is reduced here, it is reduction means it is negative only. So initial area minus final area divided by initial area into 100. Then they will ask you to find the Young's modulus or the modulus of elasticity of material. Mainly the purpose of this test is to find the Young's modulus of the given material of the specimen. So here Young's modulus, as we already know, within elastic limits, it is the ratio of direct stress to direct strain, sigma divided by epsilon. So here sigma is once again stress in the elastic limit, that is given by resistance force developed divided by the cross section area P by A, and epsilon is strain in the within elastic limits, which is given by change in length divided by initial length. So initial length I have taken L1 here. So A1 I have taken as the initial area, A2 as the final area. So A1 is given by pi D1 square by 4, A2 is given by pi D2 square by 4. So all those things, because it's a circular specimen, so they are the formula. Now, once the load is applied gradually, there will be an instrument called extensometer or dial gauge. So by the use of which we can measure the elongation. So extensometer will be having some least count, just like your slide calipers and screw gauge and all. So least count will be there for a given extensometer. Least count means it is the minimum dimension that can be measured using that particular instrument. So normally extensometer will be having, I have taken a problem here, later I can explain that. So here, using that extensometer or dial gauge, we can measure the increase in the length, and in that UTM there is a load indicator. So you have to note down two things. One is whatever load you are going to apply, you can start from 0, then in terms of newtons, then in terms of kilonewtons. Till the failure of the specimen occurs, you have to slowly, gradually, you have to apply the load. And go on calculating the stress and strain values at those load values. So stress is given by P by A1. So you know the value of P. A1 is the initial area. You can tabulate the stress values for a particular load value. Then strain value also you can calculate by knowing the extensometer reading. You can calculate the change in the increase in length delta L divided by original length, that is L1, gives the strain value. So you can tabulate stress and strain values, corresponding values. So for a particular value of P. So here L1 is constant, D1 is constant, L2 is constant, D2 is constant, P is variable. So at different values of P, you have to find out the stress values and the strain values. Then if you plot a graph, so stress value you have to take along y-axis, strain value you have to take along x-axis. You can see here epsilon. So you will get a typical graph like this. This is a typical graph, characteristic graph we can say for mild steel specimen which is subjected to tension test. So initially the graph, if you plot the points and join all the points by straight line and curves, you are going to get a curve like this. This is a typical one, theoretical graph. In the experimental part you may not get the same type of graph, but it will be identical with this. So here initially you can observe here that the graph is a straight line. So in this portion it is a straight line. Initially the graph is a straight line. Afterwards it takes a curved path. So details of this I have explained in my lecture video. You can just see that. So here initially it will be straight, then it takes a curved shape. So up to this, till that it is straight, I have taken here OQ. OQ is the straight line portion. So this Q is called as the elastic limit. So up to this, if you remove the load, this specimen regains its original length, whatever diameter it is. Then afterwards, it goes, it enters the plastic state. So elastic state is over there. Then it starts getting permanent deformation, so that even if you remove the load, it won't come back to its original length and diameter. That's all. So if you take a point here R, so that point is called as yield point. Yield point. So the material starts yielding there, then slightly reduces, then once again increases rapidly. So and it takes a maximum load at some point S. So this S point is called as the ultimate point, or the maximum stress point. Maximum stress point or ultimate point. Then it reduces, stress value reduces, and at last it fails. So that is T is the failure point. So here I have noted down. You can see M and N are the points in the elastic range. So this is the elastic range. I have taken 2 points in the along the straight line. R is the yield point, corresponding stress at the yield point. I have written here sigma y. So this is called as yield stress. Then S is the ultimate stress point. Corresponding stress here is sigma u because it is stress axis. Then failure point is sigma f. T is the failure point. Corresponding stress is sigma f there. So these stress values you can get from the graph. Now, there are 2 other things called true stress and nominal stress. So sometimes they will ask that also. True stress means at a particular load, they will ask you what is the value of true stress and nominal stress. So here, true stress is given by whatever load he has asked at, that load divided by final cross-sectional area. You can see here, A2 is the final cross-sectional area, pi u2 square by 4. Nominal stress, if they ask sigma n, sigma d is sigma n, it is load, whatever load you are given, divided by initial cross-sectional area. You can observe here, since A2 is less than A1, your sigma d will be greater than sigma n. So true stress is always greater than nominal stress. And from this elastic range, OQ, we can calculate the Young's modulus. So if you take the slope of this line, if you draw a right angle triangle here, if theta is the angle, tan theta gives the slope of this line. What is tan theta here? I have taken 2 points here, M and N. You can see here. So M, at point M, the corresponding stress is sigma 1 and the corresponding strain is epsilon 1. At the point M, corresponding stress is sigma 2, I have shown here, and corresponding strain is epsilon 2. Now, if you take this triangle, this becomes delta sigma, this becomes delta epsilon. So if you take tan theta, delta sigma divided by delta epsilon. Delta sigma means difference between these 2 stresses, sigma 2 minus sigma 1, divided by epsilon 2 minus epsilon 1, that gives the value of Young's modulus, because it is nothing but stress divided by strain within elastic limits. So OQ is the elastic limit, please note. So in this you have to take, in this region, in the straight line portion, you have to consider the slope. Slope of that line itself gives the Young's modulus here. Now I have taken a problem here. You can just to understand this concept. So in this example, initial diameter of the specimen is 22 mm and initial length or gauge length, you can call it as gauge length, is 110 mm. This is also called as gauge length. A and B, they are called as gauge points. A and B are called as gauge points here. So gauge length, least count of the extensometer 0.001 millimeter. That means using that extensometer you can measure a minimum dimension of 0.001 mm. Now tension test is conducted on that particular specimen and loads are recorded and extensometer readings are recorded. So here he has given two readings here. When the load is 22 kilonewton, load acting on the specimen is 22 kilonewton, that is P value is 22 kilonewton, the corresponding extensometer reading is 60. And when the load is 36 kilonewton, extensometer reading is 94. If you know the extensometer, by multiplying that reading by the least count of that extensometer, you will get the elongation. So here you can see 60 is the reading. LC, the least count is 0.001 mm. If you multiply that, you get 0.06 mm. That is the elongation when the load is 22 kilonewton. When the load increases, the elongation also will increase. It is 94 into 0.001, 0.094 mm. And also he has given the load at yield point. So to get this point R, when the load is 94 kilonewton, that yield point is observed. When the load is 157 kilonewton, maximum stress is observed, and final diameter of the specimen here at the end of the test, when the specimen fails, so your diameter D2 is 15 mm. So 22 mm has reduced to 15 mm, and length, increase in length is 22 mm. That means initially it was 110 mm gauge length. Now it is increased by 22 mm. That means final length is L2 is now 110 plus 22, 132 mm. So 132 mm is the final length. So instead of giving final length, he has given the increase in length. So these are the data given. What he has asked is, you have to find the Young's modulus value of the material of the specimen, yield stress value sigma y, sigma u is ultimate stress value, that is maximum stress value at the point S. There is percentage elongation, percentage reduction in area. So these things he has asked. This is a typical standard type of problem given for 8 to 10 marks in the examination. So first thing, let us find out E here. So we know this formula. E is equal to sigma 2 minus sigma 1 by epsilon 2 minus epsilon 1. Here he has given two loads. At these two loads, corresponding stress values you have to find out. So sigma 1 is P1 by A1. A1 is the initial area. Initial area only we have to take for calculating stresses. So don't confuse. So say P1 by A1. So P1 is 22 into 10 power 3 Newton. You have to convert to Newton. Divided by, so A1 is initial area pi d1 square by 4, which is d1 is nothing but 22 mm. In this problem, he has given 22 mm. Pi into d1 square by 4, you will get some value. Newton per mm square. This is the stress developed in the material when the load is 22 kilonewton. When the load is 36 kilonewton, the corresponding stress, you have to divide by the same initial. Don't take here P2 by A2. It is wrong. A2 is here is final area. But when you are calculating stress within elastic limits, you have to take the initial area only. So it is A1 only. So you are going to get some another value. So this value will be more than this. And corresponding the strain values will be, strain is defined as change in length or increase in length divided by original length. So delta L1 is this value. Delta L2 is this value we have calculated. So here you substitute that, you will get like this. Then use this formula. Young's modulus is equal to sigma 2 minus sigma 1 by epsilon 2 minus epsilon 1. So if you substitute, you will get some value here. That is also in Newton per mm square or MPa, which gives the Young's modulus value. Now he has asked you to find sigma y. Sigma y is the, what is the value of ultimate yield stress. Yield stress is given by, sigma y is given by Py divided by A1 only. So area we have to take A1 only. So second, he has asked yield stress sigma y, which is given by Py by A1 only. So Py he has given here 94 kilonewton. So 94 into 10 power 3 divided by, so area is same, pi into 22 square by 4. So simplify this, you will get the Newton per mm square. This is the yield stress value. Next, he has asked what is here? Sigma u he has asked, that is ultimate stress, maximum stress. Sigma u is the maximum, sigma max, which is given by PU by A1. So he has given here PU. Load at ultimate point as 157. So it is the maximum load that material can take into 10 power 3 divided by same 5 into 22 square by 4. So if you simplify this, you get another value in Newton per mm square. That is the ultimate stress. Then what else he has asked? Percentage elongation. Percentage elongation, as I already told, it is given by percentage elongation or percentage increase in its length is given by L2 minus L1 divided by L1, or L2 minus L1 is something but delta L divided by L1 into 100, of course, into 100, because he has asked the percentage. So this you have to multiply by 100. So what you get, delta L is 22 mm, 22 divided by L1 is 110 into 100. Okay, so this you will get in percentage. Then percentage reduction in area. For this you have to take initial area minus final area. That is A1 minus A2 divided by A1 into 100. Okay, so you know both the areas. So A1 is nothing but pi into 22 square by 4 minus A2 is pi into 15 square divided by 4. Okay, so here A1 and A2 we can easily find out and then substitute. So what I will write here is A1 is given by 5 by 4 into D1 square, that is 5 by 4 into 22 square. So you will get some millimeter square. A2 is 5 by 4 into D2 square, which is 5 by 4 into 15 square. Final diameter is given, that is also in millimeter. Once you get these two values, you substitute here and simplify, you will get the percentage reduction in area, so many percentage. So these are the things I have asked. This is a standard type of problem in tension test. Thank you.